Awesome. So thank you for the ones that came. This is the first time this kind of webinar, and I hope that we'll be able to make it ongoing. So if anyone wants to take one of the next talks, can be on whatever topic you want. I would be happy to help. So ping me. This time I chose to focus on simulation-based security, which is, to be honest, a very hard topic. So it's really in the core of cryptography, as you'll see, and I hope that this talk, so it's going to be a hard one, it's going to be very confusing. However, I try to make it educational in the sense that we're going to follow examples, and it's supposed to be somewhat intuitive, okay? However, again, I would keep reminding you that it's okay to not completely understand it, because it's really it's like the material for a full course in foundations of cryptography, right? Okay, so let's start. So this is the definition of simulation-based security or paradigm, and if you understand this definition, you basically understand everything. So I don't expect you to understand it now, but let's read it anyway. Simulation is a way of comparing what happens in the real world to what happens in an ideal world, where the primitive in question is secure by definition. Okay, so this is a proving technique where we have an ideal world, and in this ideal world, the primitive that we want to prove secure, whether it's encryption scheme, zero knowledge proof, multi-party computation, so it acts exactly as we wish it, as we want it to act, okay? And there we apply the simulator. So let's try to have some kind of a mental model of this. So let's imagine this kind of, it's a multi-party computation, so you have many parties and they are communicating with each other to compute some kind of cryptographic primitive. And this is the real world. Now, the equivalence in the ideal world is that we have this trusted party, played by Iron Man, and this ideal functionality, you can call it, actually carries out the task, the primitive that we want to do perfectly, right? Without any, like, it's doing exactly what we want it to do. And communication is done directly to this party. Okay, now it becomes interesting because we are dealing with security when we are now introducing adversary. So the adversary, played by Thanos, is this in the real world, it will just take over some of the parties or some of the participants, and in the ideal world, so here it's a bit different, because here we actually going to simulate the adversary, and the one that will be in charge of the simulation would be the simulator, okay? So the boxes is basically a simulation of the adversary. So don't worry, we'll get to exactly what does it mean, but the point here is that we want to prove, or want to show there's an equivalence between the ideal world and the real world from the perspective of the adversary. So looking from the eyes of the adversary, seeing his view, his inputs and outputs, we want to make sure that the adversary cannot distinguish between what happens in the real world and in the ideal world. And I'll give the motivation and intuition behind it afterwards, but just keep it as a mental model. As for notation, so we have the adversary is A and simulator is S, and the ideal functionality is, we note it by F, right? So let's look at a less abstracted example of zero knowledge, and this can be any zero knowledge proof, okay? So I'm very abstracted still. So we have two parties in a zero knowledge proof. We have a prover and a verifier, and both of them know a language Y, and the prover also claimed to know a witness to this language, some X that is actually a member of the language, and he wants to prove to the verifier and that he knows this witness to the language without exposing this witness. This is the essence of zero knowledge. Now, in the real world, you see that this is basically messages going back and forth between the party and the prover. And how it would look in the real world, in the ideal world. So here, it looks very different, okay? So the prover will send to the ideal functionality X and Y, and the ideal functionality will check if X is in the language Y, and will send true or false to the verifier, okay? So looking at it now from the perspective of the adversary, so the adversary, the only interesting case here is if the adversary is the verifier and he tries to learn something about the witness X, right? So as you can imagine, in zero knowledge, what we want to make sure is that the verifier will not be able to tell anything about the witness X from the proof itself. So the adversary would be the verifier, and the simulator would control the adversary, would run a simulation of it. This is the box, and what you can see is that in the ideal world, the simulator gets basically nothing. So he only knows the simulator that runs A. He only knows about the language Y, and the answer true or false given by the ideal functionality. And he needs to somehow simulate to the adversary a view that would be indistinguishable. So now you understand that if the simulator would be able to do it, it means that even without knowledge of the witness, because this is something that obviously the simulator has no knowledge of, so it means that we achieve zero knowledge. Right. Let's go to an even more concrete example, which I hope you all know, which is Schnorr protocol for discrete log. So here, we have again a zero knowledge, but a proof of knowledge. So we have a prover and a verifier. Both of them know a point age. Now, the prover also claimed to know a witness, which is the discrete log of this proof of this point age. Okay, so how the protocol would go, and I would repeat this pattern in other examples as well. So first, let's present the protocol, and let's be convinced that it actually works. So we have the prover, which will choose a random number R, and then will compute a point A. You will send this point to the verifier, and the verifier will respond with a challenge, a random challenge E. Based on this challenge E, the prover will now compute Z, which is R plus EW. Now, to convince yourself, you need to check, at this what the verifier will check, that G to the Z is equal to the point A multiplied by H to the E. Okay, so you can check it very easily and see that it works. Now, this is the correctness. I will not try to convince you that it's sound. Okay, this is another property of this type of protocols, which called sigma protocols. But I do want to look on the zero knowledge aspect. Okay, so again, zero knowledge, what it means that the adversary would control the verifier. Okay, and the simulator in this case would actually run the adversary. So let's look at the simulator here. Okay, so what the simulator knows only the point H, and he needs to convince somehow the adversary, now played by V, the verifier, that he knows the witness, okay, without him having actually knowledge of the witness. So let's see how the protocol goes. So it's very simple in this case. The simulator will choose randomly this Z and also the challenge E. And from that, he will compute a point A, okay, which has the same distribution. Okay, so if you look at it now, only on the distribution, no matter how actually it was generated, so the distribution of AZ in the real protocol and in the simulated protocol will look the same. So as you can see, the simulator actually simulates to the adversary the entire view of the world. So the simulator doesn't care, for the simulator, it doesn't care what happens in the outside world. All he cares is that the adversary would see the same distribution. Now the adversary would see the same distribution, and then comes the interesting part of the proof, right? So let's summarize kind of the observation we had so far. So the simulator would execute the adversary. He will hand the adversary a garbage that looks indistinguishable. Okay, so we just choose stuff randomly, which we call garbage, and that's supposed to be indistinguishable. And then comes the part of actually doing the proof. Okay, so what does it mean? It means that you need to actually do the mathematical operation of building a distinguisher and show that if it's actually managed to distinguish, so you are breaking some kind of some mathematical primitive, right? Something that's some assumption that you made in your system, right? So we are not going to focus on this last step, step number 3. It's a very mechanical step, and hopefully if you got the simulator right, so everything would go smoothly, even though it might be very painful to do. However, the second step and the first step, and actually building the simulator, this is kind of an art. Okay, so in cryptography, this is basically what the cryptographer would do. He would come up with a protocol, right, like we saw here. Then he would build the simulator, and then comes the step of the proof. Okay, So the proof is again just a mechanical step, but building the simulator and then the protocol is going to be iterative, right? So you need to do these steps over and over until you get it right, and you do all sorts of compromises while doing so. Because, for example, you try to do the proof, you see that you get stuck, you need to introduce something new to the protocol, and so on. So in this talk, I'm going to focus only on this building the simulator. I'm not going to actually go all the way in doing the proof. One, because it's very time consuming, and I don't think it would teach us much. I just want you to see this, to get the intuition of why this is a good proving mechanism. Okay, so going again in the now maybe one step back, because I started with giving you the mental model, but now I want to actually explain to you about the foundations of why we're actually using, or we're calling it even a simulator. So this expression is how you prove something which is semantic secure, okay? And this is to prove that an encryption scheme is actually secure. Okay, so you see that we have in the top line, you see that we have some key generation G, and then we generate a key K, and the adversary on the top line gets an encryption of something, some XN, some message, let's say, and with additional okay, thank you. So with additional parameters such as the size of the plaintext xn, and also some additional functions, some auxiliary function h. Now, what we want to prove here is that this adversary cannot compute anything useful, some function f of the plaintext, better than some other adversary a prime, which is not even given the ciphertext e. Right. So if you see on the line below, for every, so the right way to read it is that for every adversary A that can learn something on the plaintext, there's an adversary from the ciphertext, there's an adversary A prime, which can learn something even better, right? Or at the same probability of some distribution. So it makes sense, I assume, right? You see that there's an adversary that gets nothing, and it can learn the same for every adversary that gets the ciphertext. However, let's stop here for a second and ask ourselves if this is actually the right way to write it, because intuitively, if I would ask you before, can you come up with the way to think about what's a secure encryption, you'd ignore completely from the bottom line, and you can just take the top line and say this should be very, very small, right? The probability of producing some valuable insight on the plaintext given the ciphertext should be negligible, right? Okay, so why we are not using this one, and instead we're using this more complex expression? So there are two reasons. One is that it will not be secure as you think so, because there are all sorts of cases that I'm not going to, that for encryption schemes that obviously are not secure, but would succeed in this upper line is a negligible probability. And the other one, which is more important to understand, is that we don't have the tools as cryptographers to actually prove the second statement that the upper line is negligible. We don't have. Eventually, if you try to write a proof for it, you get stuck because it's not reducible to anything mathematical. However, once you go and write the expression of semantic security and it's like it's written here, then you can come up with a tool. And what does it mean? So if you look closely on the line below, on the expression at the bottom, you see that this is some instantiation of the ideal world, right? So this A prime is basically a simulator, okay, right? So he gets nothing, and he somehow needs to produce the garbage that would come up with a better probability. But there's a very hard question here, and this is written down there. How can this A prime even know what A is doing, right? Because look, this expression says, and I know it's not very easy to understand it, and believe me, there is a course for in Foundations of Cryptography that spends like a few hours just on this expression. But what does it say? It says that for every adversary A, you can come up with an adversary A prime that is doing a better job without getting exposure to the ciphertext. So how come A prime knows what A is going to do? And the answer is that it's basically going to run A. Is going to simulate A. Okay, so what the simulator A prime would going to do is basically going to run A with some input. Okay, and this is, I think, the source of the name simulator, because you need to run like the adversary. This is what you need to simulate it. So let's look at this concrete example. What's the simulator here? So A prime as input, you see that it gets just some security parameter and the size of the plaintext and some auxiliary function known also to A. And A prime will run the key generation and will receive some random key, doesn't matter. It would encrypt garbage, right? So here I'm using 0, just a string of zeros for the ciphertext. And by the way, look, pay attention that these two first line in the simulator actually uses the fact that we have as input 1 to the n and the size of the plaintext, just as an FYI. And then here comes the interesting part. So A prime would run A using this garbage ciphertext, okay? And would output whatever A outputs. And I hope that you can convince yourself that unless, again, you go to the proof stage, but unless there's something wrong in the way you designed your encryption scheme, you shouldn't be able to tell. So A prime will do at least a good job as A is doing, okay? Just to be more concrete, let's say that your encryption scheme is some kind of XOR with some random number. So what you're going to show is that unless your PRF is secure, so you can reduce it to PRF security. So unless your PRF secure is insecure, sorry, you cannot do a better job distinguishing between the two cases, right? So I hope that it gives you kind of the intuition, okay? Okay, let's go on and try to look at the simulator from more the engineering perspective, okay? So this might be another view of the simulator. So basically, a simulator is a program, and this program is running another program, which is the adversary, okay? So we are in computer science, so we can deal with programs. But what does it mean? What can we learn from the fact that those are basically two programs? So first, program S actually calls program A. So it's like a main that calls some routine A, okay? Now, what it means is that for any edge case that may come up with the program A, S must define his behavior, right? So A can do whatever he wants. He can abort in the middle. He can insert some invalid inputs, whatever he wants. And for each one of these cases, the simulator S must come up with something which is well defined, right? So, otherwise, like, our program would crash. Another interesting thing is that the simulator S, you can think about it as kind of like a virtual machine. So the A is basically a virtual machine running over the host S. So S is the host. So it means that S can provide the inputs for like the input tape and random tape is what's called computer science, but like the inputs for A program. And the most interesting part, for those of you that have done some reverse engineering, that it will be more familiar. So S can do a rewind for the program A. So right, imagine that you are using some GDB or some debugger, and you get to a point in your program and you stop it. You put a breakpoint, and then you are rewinding it and starting it from a different point, right? So the simulator can actually do it for the adversary. So I'm not going to go into the full details of why this is actually secure, but when you think about it from the engineering perspective, it's okay. Okay, let's move on to another example. This is a classical one, another zero knowledge. So we're still in the world of zero knowledge where we have two parties, prover and verifier, and this example is the three coloring. So just to go over the problem statement, again, we have a prover and a verifier, and prover is, and both of them know, both of them get a graph G of nodes V and edges E, and the prover, in addition, has some mapping, some side mapping of colors or numbers 1, 2, 3, such that for each edge in the graph, the two nodes that compose this edge have different colors from 1, 2, and 3. Okay, so let's first look at the protocol, and yeah. So the protocol, it's this protocol, but it would be repeated many times, like polynomial. It's a polynomial number of times, which equal to n times the size of the edge, number of edges. Okay, but let's look at a single run. So the prover would first come up with a permutation of the mapping. Okay, so this is phi of V. And then he would compute commitments. Okay, this is like the cryptographic primitive here that eventually the security would rely on. So he computes these commitments to all of the nodes, and he sends all of the commitments to the verifier. The verifier, as we saw before, produces a challenge. This time, this challenge is not completely random, but it's a specific edge from the graph. And what the prover would do, it would decommit to both the nodes that compose this edge, okay? And then the verifier would basically check that the commitment was done correctly and that the colors are from 1 to 3 and that the colors are different between the two nodes, okay? And try to convince yourself that if you are repeating this over and over again for many times, the probability that the prover actually cheating you is very small. But again, we're not dealing with soundness. We want to focus on simulation, okay? So as before, in zero knowledge case, we are more interested to see what happens when the adversary controls the verifier and try to learn something about the mapping that is not supposed to know. Okay, and so let's look at the simulator in this case. So again, the simulator gets the graph and this kind of access to, now it's called V star, which is the adversary, okay? So the simulator would repeat many times again, and this is how it works. So the simulator would choose a random edge, E prime, and for the two nodes of this edge, you would pick different colors for them from 1, 2, and 3. For all the other edges, for all the other nodes, you just pick the number 0 or some invalid color, okay? It doesn't really matter. And then you will do, you will send commitments to V star, okay? So as you can see, the API, the interface that the verifier sees is, the first step is commitments, okay? So in the real protocol, he gets commitments, and in the simulator, he also gets only the commitments. So it's okay, right? So if you are looking from the standpoint, point of view of the adversary of V star, you get commitments in both cases. Now, because commitments are secure and like you give you the intuition, because commitments are like binding and hiding, so this will be also secure, right? He cannot learn anything different. So because of that, the simulator, the adversary V star will just respond with a challenge, right? Some edge. Now there are two cases here. What happens if the edge that the adversary chose is equal to E prime, to the edge that S chooses randomly? In this case, we are good because we know that this is going to be a valid decommitment. So S just complete the iteration. But however, what happens in the case where E is not equal to E prime? In this case, the simulator can just rewind. Okay, so he stops and he returns to the to step 1 where I need to choose a different edge E prime. Okay, so again, from the adversary perspective, nothing wrong happened because his program runs as usual, so he cannot distinguish anything. You just clear his memory from a certain point until some earlier point, and then you start to run it again. And try to imagine what happens when you run it many, many times. So the probability, if you're going to run it many, many times, is that eventually you will hit this line 3. Okay, so eventually the adversary would see the same views, and therefore we can go and prove the security. Okay. Now, a few things about it. First, I'm not mentioning the time aspect. So if you compare the real world and the ideal world in terms of time of running, so I'm not sure if it will be the same. However, let's put it aside. Also, try to think for yourself what happens if you want to run this same zero knowledge proof many times in parallel. Okay, so everyone is still here and he can hear me? A second. Everyone can hear me? So, as I said, some network issues. Okay, so hello Ishmael. So I'm continuing, okay? So let me share the screen again. Can you see the screen? Okay, so I'm continuing. Let me know if there's a problem. So try to imagine what happens if someone wants to run in parallel many times the same protocol. And because of this many repetitions, I will tell you that it will not going to work. So this is like the time when you need to do this kind of iteration where you need to adjust the protocol and then adjust the simulator and so on. So keep it as a challenge for later. Okay, so now we can move to MPC. How MPC is different. Now parties are doing something which is a bit more complex. So instead of a prover and a verifier, we have many participants. Each one of the participants or the parties will have his own input, and each one will supposed to get an output. Security notion here is more, it means privacy instead of earlier what you saw with zero knowledge, which is the zero knowledge property. And basically what it means is that you don't want, you want to compute some function and you don't want to expose your input while doing so, okay? So in the two-party case, let's go over the execution really quick in the ideal model. Again, just to give you the mental model again. So both of the parties send input to the trusted party or the ideal functionality. This ideal functionality will compute a function, right? So you can do everything, just it takes input and compute a function. There's an early abort option. I mean, there's no guaranteed output delivery in two-party computation with malicious adversaries. So it means that the adversary can decide if at this point there's an abort. If he decides to not abort, so trusted party would send output first to the adversary. Then the adversary can decide if the trusted party can also send the output to other honest parties. Okay, but what's important to get in mind is this model. So first we have parties that sends their input to this ideal functionality. The ideal functionality compute the function and sends the output. Okay, great. So this is becoming really complex very fast, and now and because of that I want to focus on a specific protocol, which is the simplest MPC protocol you can come up with, which is basically a coin toss between two parties. Okay, and you'll see in a second why simulation can become very not intuitive and more of an art. Okay, so let's first describe the protocol, and it's very simple. So party 1, P1, Spider-Man would choose a random number R and a random bit B1. He would compute a commitment to this bit C and would send this commitment to P2, to party 2. Party 2 would randomly choose a bit B2 and will send it back to P1. P1 can now compute the random bit, which will be B1 XOR B2. And if he chooses to, he can send a decommitment B1 and R to P2, and then P2 can also compute the same bit. Okay, so in this case, when we want to describe the simulation, so here we have two cases, right? So adversary can control either P1 or P2, right? If adversary controls both of them, it doesn't really interesting for us, but let's see what happens in each of the cases. So let's start with the simpler case where the adversary is controlling party 2, right? The one on the right, Ironman. Okay, so you can see that the interface the adversary should simulate here is this commitment and then decommitment. Sounds very easy. Now the ideal functionality, as I said, is doing everything. So ideal functionality actually takes no input, right? So just like 1 to the n. And the ideal functionality F supposed to output a bit U1, so it's a random bit. It's supposed to be the same one for both P1 and P2. Okay, so this is how the simulation works. the simulator starts by engaging with the ideal functionality and get back a bit B. So remember, the simulator doesn't have to play by any rules besides the fact that it needs to make sure that the adversary sees the same. Wait a second. Slides are stuck for everyone, or just for or not? Do you see the simulator for slide number 27? Let me try and share the screen again. Okay, great. So now you see 27. So it means that I guess many of the slides. Okay, so it's not that bad. So just to give you eyes of what we discussed. So there is the MPC execution. There is the mental model that you should be keep in mind, and then there's this protocol, which is luckily very simple, about the coin toss. So thank you for the for this. Otherwise, could have gone much worse. So now I'm describing the simulator, and what I'm trying to say is that the simulator should basically simulate the same API, the same view that party 2 is seeing. So party 2 is now corrupted, and the simulator runs party 2 and should give it the same. And what I'm trying to say is the simulator does not have to obey any rules. Okay, so it doesn't have to communicate with anyone. The only thing it needs to do is to make sure that the adversary gets the same, cannot distinguish between this view and the view in the real protocol, right? In this protocol. So what it will do, the simulator, so it would engage with the ideal functionality and receive back a bit B. So this is the output, okay? This is already the output, and now the simulator knows the output, and it's fine. There's also a technical issue where the simulator should maintain some counter. And now what the simulator will do, so simulator would invoke this adversary or party 2, P2. He will choose a random bit B1 and some random number R, and it will hand the adversary the commitment, okay? So until here everything is nice and well. You see that in both cases commitment is sent in the real protocol and also in the simulator, right? So everything fine. Now, because we already know the output bit B, if the adversary would reply with B2, which is actually the right one, right? So if you do the XOR between B1 and B, you should get this B2. So it's good. It means that the commitment would be valid, so the simulator can decommit. And of course, there's no way for the adversary to, as long as the commitment is secured, the adversary will not be able to distinguish. However, if it's not the case, so then we need to do some kind of another rewinding. So we rewind again and then repeat. And we get to do it n times. And as you can see, it will be very small probability that we will not hit this step number 3 within n tries, okay? Because it's just a single bit, okay? By the way, it will not work, this protocol, for a string of bits. It's just for a single bit. Yeah, so this is it. Again, we see the rewinding. And just wanted to say that this is supposed to show you the privacy property, because as you can see, the simulator doesn't know anything about the inputs. All right, in MPC, you want to make sure the simulator doesn't get any input, and still just using what it do gets, it needs to somehow simulate to the adversary the right view. Okay, so now really quick, I want to go over the other case where party 1 is the where party 1 is malicious. Yeah, so I see there's a question about why it will not work for string of bits. So it will not work, again, the intuition is, I think, the same one as why it will not work for multiple 3 coloring. I mean, the fact that we are doing this repetition would work when it's single bit, but trying to do many of them in parallel would make this probability, would make the probability that we actually get all of them correct very small. But let's keep it for afterwards or offline, because this is a great question, but out of scope a bit. So just let me quickly say something about the adversary in this case where it controls P1. So keep in mind, this is supposed to be super easy, and if I would ask you just to think about yourself the simulator, I guess that you can come up with something on your own, right? The simulator so is running or simulating P1, and the only thing it needs to simulate is this bit2, right? So this is supposed to be easy. However, it's not very intuitive. So if we look at how it looks, I'm sure that it's going to be very different than what you originally thought of. So again, the simulator would invoke this ideal functionality and we'll get the output B. Then the simulator would invoke the adversary A 3 times, okay? So now this is a good example to the fact that this is a program running a program. So the simulator can decide, the program A is deterministic, okay? And the simulator can decide what is exactly the inputs, but what's important is that A is deterministic. So the simulator would run 3 times the adversary, each time so first time you would run it, you would test it with the bit B2 equal to 0. Second time you would run it with B2 equal to 1. And for the third time, you would need to make a decision on what on which bit to send it based on the answers. So this again try to cover all of the edge cases that the adversary can come up with. Okay. So I'm not going to details here, but let you guys go over it and see for yourself that everything is covered. But this is completely non-intuitive, at least for me. Maybe for you it is. Few words on universal composability. So we encountered universal composability nowadays in many of the security proofs. So this is kind of an evolution of the simulation technique, and so far we focused in simulation on a standalone. Okay, so what happens if there's a protocol and I want to run it just once, and this is why we could have described everything we've done so far. However, in universal composability, I want to be able to compose different protocols, to run them concurrently. And what it means is that I need to introduce this environment machine. So this is a new machine, another program that actually controls all of the simulators, right? Or controls all of the other programs. So it means that, for example, rewinding is not possible, right? Because it's not that I can rewind a program, because there is another program that controls me, right? Something like this. Also, a nice result about it is that UC is impossible, at least in the, let's look at the two-party case, without a trusted setup. So everything that is proven secure in UC is must use some trusted setup. So it's very interesting. And yeah, I think that concludes my talk. I want to summarize by saying kind of like the roles of the simulator, repeating it, and you can later go over earlier slides and convince yourself that everything clicks. So the simulator should generate a view. Should generate a view for the real adversary distinguishable for its real view. The simulator must extract the effective inputs used by the adversary in the execution, and the simulator must make the view generated to be consistent with the output is based on this input. So try to convince yourself that those 3 elements indeed happened in all of the examples we saw. Yeah, so that's it. I'm open to questions. I can take them, I think would be more efficient in the Telegram group or as direct DM. I'm not sure how the video would come up eventually. Maybe I'll try to do like an offline run, just me speaking with good connectivity, and then build it and then publish it. Anyway, we'll be happy to hear your thoughts later on, and thank you for joining, and I hope that I will be able to make a tradition of these webinars. So great, thank you.